Good day, and welcome to Africa Teen Gigs. And we present to you the STEM Digital School. I hope that everybody is doing well and is okay and is ready for the grade 12 physical sciences class. Yes, indeed. My name is Nonkulego Madondo. As you can see, my picture on the right hand corner. And I am your physical sciences grade 11 teacher. Today, however, we're going to be doing conservation of energy. Yes, we're still going through the program of work, energy, and power. So, if you have been following through, this is what we're going to be doing today. And we've been doing quite a lot, eh? I hope that everybody is coming along fine and is getting to understand everything that is happening because for grade 12, unfortunately, nothing has been amended. Everything is the way it is. You have to know all your problems, your theories and everything that has been done in grade 11 syllabus 2020. Yes, indeed. Just reminding you that I am working from the Siavula textbook and the study and master textbook. So if you want to follow through with those textbooks, you just can get them on Snaplify. They're absolutely free. You can get them. You just download the application and you can download any subject that you need. Okay. Then moving through. So going back to our homework, I gave you guys homework. Remember we did the work-energy theorem yesterday. So this is the problem that we did. So it says on number one, a pendulum of 300 grams is attached to the ceiling. It is pulling up to a point A, which is a height of 30 centimeters from the equilibrium position. Calculate the speed of the pendulum when it reaches point B. Assume that there are no conservative forces acting on the pendulum. So, what does this mean? This is another word for actually saying it's a frictionless, you know, it's a frictionless pendulum, okay? Because non-conservative force, if you remember when we did the definitions, friction is an example of a non-conservative force, okay? So we can apply the work energy theorem in this case. The only force that does not work on the pendulum is that does work on the pendulum is gravity. So here we're dealing with conservative energy, and we know when you do conservative energy, we're talking about the gravitational potential energy. Okay, so from the conservation of mechanical energy, that the change in gravitational potential energy will correspond to the opposite change in kinetic energy. That is, if gravitational potential energy decreases by an amount, kinetic energy will increase by the same amount. Okay, what does this mean basically? It means that you've got HO and H1, okay, on HO it's probably going to be on the bottom. There is no kinetic energy at the bottom, so you will have potential energy, but when it reaches the top, you probably have kinetic energy and zero potential energy. Basically, that's what it means, that they swap places, because with this potential energy, there will probably be zero kinetic energy. So what we do first here, you're going to check what is given to you. And if you look at here, you can see that it's not in the standard units. So for mass, you have to change it to 0.3 gram, and the height, you must change it to 0.3 meters. Okay, so you always have to convert before you do a calculation so that you do not get confused. Okay, so here we are. So what they've done here, basically, they've said kinetic energy, the change in kinetic energy is equals to the change in potential energy. And what does that mean? It means that PE, PI, PF, PEF, potential energy final minus potential energy initial is equals to kinetic energy final minus kinetic energy initial. So what they've done here, they've just swapped and changed them to put the initial ones together and the final ones together. Okay, so we know in the initial point kinetic energy is 0, so at least this one we've already dealt with it. So now we've got mgh final and mgh initial and kinetic energy. What are we looking for here? Here we are looking for the velocity, and we know that we're going to find velocity on our kinetic energy formula. So what we're going to do here, we're going to put these ones together, and here there should be an equal sign, guys. I'm sorry, I forgot to put it in there. Mg Hi minus Hf, okay, will be equals to half mv squared. Okay, then we divide both sides by m in order to have the g Hi minus Hf is equals to half v squared. Okay, are we together? Then from there, we can substitute what we have, and it will be 2g times, this g is 9.8, times the change in f is this 30, and it's 0.3 meters, and that will be v squared, and that's how you get your answer. You see, it's all about knowing which formula you need to apply. And if you know what formula you need to apply, then everything becomes so much easier. Okay, so there's another question that I also wanted us to do. I also got it from the Siavola textbook. It says the driver of a 1,000 kilogram car is traveling at a speed of 16.7 meters per second minus 1, applies the car brakes when he sees the red light. Okay, so the car's brakes provide a frictional force of 8,000 newtons. Determine the stopping distance of the car. Okay, so first of all, we need to write what do we have. Okay, so what do we have in this case? We've got the speed, which is in meters per second minus 1, and we've got the mass of the driver, which is 1,000 kilogram, and we've got the frictional force, which is 800 newton. So we are required to determine the stopping distance of the car. So how do we apply that? We will apply once again the work energy theorem. We know that all the car's kinetic energy is lost to friction. Therefore, the change in the car's kinetic energy is equal to the work done by the frictional force of the car's brake. Basically, this is the equation that we're going to use. Remember, work net can also be equals to the change in kinetic energy. Therefore, we first need to determine the car's kinetic energy at the moment they use the brake, and that's going to be EK is equals to half mv squared. This energy is equals to the work done by the brakes. We have the force applied by the brakes, and we can use the work is equals to if change in x cos theta. Okay, and what are we looking for? We're looking for this one here. So we can try and get all that we need in both sides in order for us to get the x. Okay, so now we determine the kinetic energy of the car. We're doing it separately so that we can be able to avoid having to have too many calculations. So it's going to be half m, its mass is 1,000, and the velocity is 16.7 that was given to us. Now you have your potential energy. So to determine the work done, you can either do it like this, or you can just plot it both in the equation and say work done is equals to triangle EK. So in this case, we plot everything, and remember, because it's frictional force, it has to have -1, which is a cos 180 degrees. Do not forget that, guys. And remember that this as well, it's our non-conservative formula. Okay, non-conservative force formula. So it's going to be minus 8,000 triangle x, and this change in distance is what we are looking for. Okay, then we come here and we're going to say change in potential kinetic energy is equals to the net work that has been done. So you're going to substitute all of this, and you will have your change in x on one side, and this is your answer. So the car stops in 17.4 meters. Guys, I hope that everybody understands. I just wanted to do enough problems with the work energy theorem so that you guys understand it, because it's got very different formulas and different ways that it could be asked. But I hope these two ways, they indeed help you guys. Okay, so today we're going to do conservation of energy, conservative force work. We're going to do the work done, and the non-conservative force, we're going to do the work done on that too. Okay, So, conservation of energy. It says here when an object is free falling, the mechanical energy is conserved. This is to say that the gravitational potential energy is the only force that is acting during a free fall. Okay, which makes sense because it's on the air, it falls down, and there's nothing else that's preventing it or stopping it, for example. Okay, so mechanical energy has 2 points during a free fall in the same time is the same. Okay, mechanical energy at 2 points. So which means if it could be here or could be here, the mechanical energy is going to be the same in both times. Okay, so a conservative energy always results in stored or potential energy. So what is a conservative force? Conservative force is one for which work done by or against it depends on the starting and ending point of a motion and not on the path taken. Okay, so if any object is sliding or free falling along a frictionless path, no non-conservative force will be applied to it. Okay, a non-conservative force in this case we're talking about friction or air resistance, all those stuff. Okay, so the only force will be the conservative force, which is the gravitational force. The following equation, work net work non-conservative is equals to ek plus ep, and work non-conservative will be equal to 0. You get me? So when there's 0, um non-conservative energy, it becomes a 0, and in this case we'll say minus change in potential energy is equals to change in kinetic energy. So I'm trying to show you guys how this equation came about. So they equated to 0 and they put them in different sides, and so now we've got the E potential energy final and initial, and on that side we've got E kinetic energy final and E kinetic energy initial. So you see, I'm basically reversing back from how we got some of the formulas that we also did on the other side. Okay, then this is what we end up having. We have E potential initial minus E potential final is equals to E kinetic final minus E kinetic initial, and then we like the initial terms together, so it's going to be EPI plus EKI will give you E potential final and E kinetic final. Okay, or this is basically what you can do. So you see how they got this formula. Remember that time we were also working with a frictionless a pendulum. A pendulum is also frictionless, so that's why we got to use this formula here, because the work non-conservative energy is 0. Okay, let me show you quickly. You see here, this is why we got to use this one, because our work non-conservative was 0. Okay, and now we still continue with conservative force when we talk about pushing a ball up a slope. Okay, so it can happen that you find problems like that. So the slope of length d is the hypotenuse of an imaginary right angle. Okay, so the work done by gravity while pushing the ball that has a mass m up the slope can be calculated. So this is what will happen if they talk about pushing a ball up a slope. This is basically the imaginary triangle that we'll have. Okay, so the component of the gravitational force parallel to the slope is FGX and FG. So if you check here, this is our ball, this is the normal energy, and this is um, the applied force. Okay, and then what we'll also have the gravitational force, right? But we're going to make it have two components, and the component that it's parallel to this one will be the Fx. You see, so this one is the parallel to the distance. Remember, we always use the force that's parallel to the distance. So in this case, it's going to be Fgx. And this Fgx is what we're going to use. But if you check here, this Fgx is going on an opposite direction. So which means that this will act sort of like a frictional force. So which will, because it will become a minus. you see, when we put it in the formula, it becomes a minus. So we're not going to use this normal force because it's perpendicular to the distance, okay, of the object traveled. So we're only going to have this FGX. And in this case, it's going to be a minus FG sine theta d minus 1. It's going to be a sine theta in this case. It's not going to be a cos theta, because remember, sine theta is what is opposite hypotenuse. I mean, it's opposite over hypotenuse. Okay, opposite over hypotenuse is sine theta. So in this case, we're not going to use cos theta. We're going to use sine theta, and then d is our distance, and that is times minus 1. Okay, and this is what you're going to get. It's going to be a minus. So we can take this sine theta as well and break it down to say opposite over hypotenuse. And remember, we also have our d. So it's going to be h over d times d, and then you're going to cancel out the d's. Okay, and then from there you're going to have minus FGH. Okay, so it's simple to see. Basically, you just use your work done formula, and you're just going to substitute everything, because this is a force, this is a distance or displacement, and this is a cos phi. So we do not have the distance, and we can substitute FG sine theta to the F, and then the cos is minus 1, because it's a negative. It's minus 180. It's cos 180, so it's going to be minus 1, and this is what you're going to have. So the result shows that the problem is independent of the angle of the slope, and the displacement is cancelled out. Okay, this means that the work done by gravity will be the same for a ball moving up any slope, because the endpoint position is at the same height. So the total work done is related to the height of the slope. Okay, so this one plays an important part, and everything else, it's independent of the angle, and it's also independent of the distance. So the height is what matters. Okay, so the total work done by a conservative force results in potential energy. If the conservative force does positive work, then the change in potential energy will be negative. So therefore, work conservative is equals to the minus change in potential energy. Okay, so now we're moving to the non-conservative force. A non-conservative force is one for which work done on an object depends on the path taken by the object. Okay, so total energy is always conserved even in the non-conservative force. The non-conservative means that mechanical energy isn't conserved in a specific system. Energy has been irreversibly transferred. An example of conservative force is friction. It removes energy from the system, resulting in mechanical energy not being conserved. So non-conservative energy can also be positive and increase the mechanical energy in the system. So for example, F net force, the net force is equals to F conservative plus F non-conservative. And the work done by these forces yields. Okay, so work net is also going to be the same. It's going to be work conservative plus work non-conservative, and in here we're going to be using the work energy theorem. So in this case, it's going to be change in kinetic energy is equals to, because remember, work net is also equals to change in kinetic energy, and that will be work conservative plus work non-conservative. So using the work conservative is equals to minus PE. We're going to have change in K is equals to minus E, change in potential energy, plus work non-conservative. So work non-conservative will always be change in K plus change in EP. I hope that everybody's following. So here is an example that we can use. Okay, a 60 kilogram scale. Basically this, I'm going to give it to you guys as homework, and I hope that you guys will all be able to do it. It says a 60 kilogram skier with a initial speed of 12 kilometers per second coasts up a 2.5 meters high rise as shown in the figure. Find her final speed at the top, given that the coefficient of friction between the skis and the snow is 0.8. Okay, so find the distance traveled up the inclined, assuming a straight line path as shown on the figure. Okay, so we need to determine the length of the slope, as this distance over the friction acts as well as the normal force of the skier on the slope to determine the magnitude of the force due to friction. So the normal force balances the components of gravity perpendicular to the slope. So guys, I need you guys to go for me and do this problem, okay? And why do we need to do this problem? So that we can test ourselves. You can be able to test yourself if you know how to do this workforce energy, because these things are very complicated, especially if you do not understand them. Number one, you need to know what is the formula for work non-conservative, which in this case we know it's change in ek plus change in ep. You need to know what is work net, which is the change in kinetic energy. You need to know what is the work conservative, which in this case ek is equals to minus e potential, EP potential, change in ek is equals to change in E potential energy minus. Okay, so these are formulas that you must know, and what's good is that you guys can write them down and see if you can memorize them, because every problem requires either one of the formula or a mixture of formulas of all the work that we've done since we started this chapter. So make sure guys that you guys know how to do these problems. But before we do that, please guys, this one, you need to determine the length of the slope as its distance over which friction acts, as well as the normal force of the skier on the slope to determine the magnitude of the force due to friction. So the normal force balances the component of gravity perpendicular to the slope. I'm not going to do this problem with you. I want you guys to go and try it out, so that tomorrow, I mean on Monday when we come back, we can go through it, and then I'll start explaining. But it'll be good if I explain something that you have attempted, because you'll be able to see where you're getting stuck, where you're getting lost, where your answers are going wrong. So that's the most important part, is for you guys to understand. So guys, I hope you've written this question down, and let's try and attempt it, guys. Let's see if we can get the correct answer. My name is Nonkulego Madondo. This is a digital STEM school, and I am your physical sciences grade 12 teacher. I hope that you guys are understanding everything that we're doing here. If you have any questions or queries, you can get me on t33tndlovu at gmail.com, and you can ask me any question. And don't forget, guys, to do your homework, because your homework is how you learn or know where you are getting stuck as a student. And please guys, do your homework, and tomorrow on Monday we're going to be continuing with this chapter. It's quite a long chapter, and we're moving slow just to make sure that you get to understand thoroughly what is happening. What is non-conservative force? You need to know what is non-conservative force, what is work energy theorem. Those are the things that you need to challenge yourself and start asking yourself little by little, so that you guys can understand, because these things are things that you're supposed to know and understand, not just cram for the exam, because it's not going to work. This is matric, guys. You need to make sure that everything that you do is on point. But for today, our class has ended, and thank you guys.